Hello, my name is Taesoo. I thank organizers for giving me this opportunity. I will talk about electromagnetic radiation from correlated charm and bottom. And my collaborators for this study are Pierre Moreau and Wolfgang Kassing and Elena Brakowskaya. Yeah, this is en route of my talk. First, I will give you a short introduction and then explain about single electron from heavy flavor in Patton-Hadron string dynamics, and then dielectron, and then summary. Yeah, short introduction. Heavy flavor has a couple of advantages as a probe particle. Firstly, large energy momentum transfer is needed for the production. So PQCD is applicable and model independent. And also heavy flavor is early produced, so it probes nuclear matter from the initial stage of heavy ion collisions. And also heavy flavor is less thermalized than light flavors. So the memory time is longer. In other words, the information of the early matter is not completely washed out. And the single electron and the part of dielectron are produced through weak decays of heavy flavors. And that is my topic. Let me first talk about single electron from heavy flavors. This is a schematic figure how a single electron is produced in heavy ion collisions. Firstly, heavy quark pair is produced through baryon-baryon hard collision. And then this heavy quark and anti-quark interact with partons in Quark-Gluon plasma. And then at critical temperature, they hadronize into heavy meson and heavy anti-meson. And then they have hadron interaction in hadron gas phase. And then after freeze out, this meson produce a single electron through weak decay. And weak decay width is very narrow, so mostly it happens after freeze out. And I will explain this processes step by step. I mean, how these processes are realized in Patton-Hadron string dynamics. Yeah, firstly, let me talk about heavy quark production. This is a cross-section for charm production in proton-proton collisions as a function of collision energy. We parameterize this several experimental data with this blue line. And then you can extend it to heavy ion collisions, multiplying by a number of binary collisions and dividing by nuclear-nucleon inelastic scattering cross-section. We obtain the number of charm pairs produced in heavy ion collisions. So now we know how many charm pairs is produced. 2 pairs or 3 pairs or 10 pairs. And then we should assign energy momentum to each charm and anti-charm. For this purpose, we use PTA event generator, but we rescale this transverse momentum and the rapidity of a charm and anti-charm such that transverse momentum spectrum and the rapid distribution of charm could be similar to those from Foner calculations. And the left figure is PT spectrum of charm and bottom from Foner calculations and from our rescaled PCA. And they are not completely identical, but they are very similar. I mean, and the right figure is momentum rapidity distribution of charm and bottom. And this heavy quark hadronizes through emitting soft gluons. This is called fragmentation. we use this Peterson's fragmentation function. And Z is momentum fraction of heavy hadron to heavy quark. And epsilon Q is a parameter, which is 0.01 for charm and 0.004 for bottom. And the lower figure is this Peterson's fragmentation function as a function of Z. And we can see this function is peaked near 1. The reason is following. Charm or bottom is very massive. So even though it emits soft gluons, the momentum does not change much. Still, lots of momentum is still in heavy quark, heavy hadron. That is why momentum, this fragmentation function is peaked near 1, especially so for bottom. And then we know the momentum of hadronized heavy meson or heavy baryon, and then we should assign species. We should decide chemistry. And charm quark could be D plus or D0 or D star plus, D star 0, DS, and lambda C. And with these different percentages. And these percentages are universal and do not depend on any dynamics like charm momentum or any dynamic quantity do not affect these percentages. And also bottom can be B minus or B0 bar or B0 bar S or lambda B with these percentages. And this is the comparison with experimental data in PP collisions at 2.76 TeV. And we can see good agreement with the experimental data. This is D0, D plus, and the D star plus. And then let me show you weak decay of heavy flavor to single electron. Single electron is produced through weak decay like D bar to K bar plus single electron and anti-neutrino, or D bar to K star bar plus single electron neutrino, or B meson to D meson, single electron and anti-neutrino. The mass difference between D meson and K-on or K star is around 1 GeV. So the momentum distribution of a single electron is between 0 to 1 GeV. But the mass difference between B meson and D meson is around 3 GeV. So it is this electron is much more energetic than single electron from D meson decay. And the right figure is PT spectrum of a single electron. The green line is single electron from charm decay, and green line is single electron from bottom decay. And the red line is some of them. And we can see good agreement with the experimental data. This is PP collision at 200 GeV, and this is 62 GeV. And we can see at low transverse momentum, charm, single electron from charm is dominant. And at large transverse momentum, single electron from bottom decay is dominant. The reason is this figure. The single electron from B decay is much more energetic, so it can easily reach a high PP region. That is why B decay is dominant at large transverse momentum. And if we study heavy ion collisions or proton nucleus collision, we should include cold nuclear metal effects like shadowing effects and cloning effects. Shadowing effect is the modification of parton distribution function in nucleus. For example, heavy flavor is produced by gluon-gluon fusion or QQ by annihilation in the leading order PQCD. And if gluon distribution or quark distributions are modified in nucleus, then this heavy flavor must be modified. And we used EPS09 package. And the Crony effect is the enhancement of transverse momentum of produced heavy quark pair because of proton nucleon scattering in heavy ion collisions or proton nucleus collision. And this photon is responsible for heavy quark production. And this photon gains additional transverse momentum through this scattering. And this additional transverse momentum is transferred to produce the heavy quark pair. Yeah, that is Crony effect. And let me show you one example. This is R deuteron gold at 200 GeV of a single electron in mid rapidity and single muon in forward and backward rapidities. This blue line is R deuteron gold without cold nuclear matter. And the red line, including shadowing effect, and the magenta line includes both shadowing and Crony effects. And we can see little enhancement in mid rapidity. And in forward backward rapidities, if we do not include cold nuclear matter effects, R deuteron gold is, similar whether it is in backward rapidity or forward rapidity. But including cold nuclear matter effects, they are split into upper lines and lower lines. The reason is following. Yeah, this is gold nucleus, and this is deuteron. Deuteron moves in positive direction, and gold in a negative direction. So if charm pair is produced in forward rapidity, it corresponds to small x of gold nucleus. So charm production is suppressed due to a shadowing effect. But if charm pair is produced in backward rapidity, then it corresponds to a large x of nucleus momentum. So charm production is enhanced due to anti-shadowing. That is why these R deuteron gold are split into upper lines and lower lines. The upper lines is forward, and lower lines are upper lines are backward, and lower lines are forward. And in heavy ion collisions, we should include also hot nuclear matter effects, which include photonic interactions and hadronization and hadronic interactions. For photonic interactions, we use so-called dynamical quasi-particle model. In this model, heavy quark interact with massive off-shell quarks or massive off-shell gluons. And this strong coupling depends on temperature, and the exchanged gluon is off-shell massive gluon. So we don't have any divergence problem. And the hadronization is one of the issues of this workshop. And for hadronic interactions, we use T-matrix calculations from effective chiral Lagrangian. This this red one is simple transition amplitude from chiral Lagrangian, and we can improve this transition amplitude by using this iteration. And this blue one is the unitarized and improved transition amplitude. And let me talk about our hadronization in heavy ion collisions. The coalescence model, we use coalescence model. The coalescence probability is proportional to a Wigner function. And this is Wigner function for S state, angular momentum equals 0. And R is relative position. R1 is position of charm, and R2 is position of anti-light quark. And P is relative momentum. And these R and P are not Lorentz invariant, so we should specify frame, and it should be calculated in center mass frame. And this sigma is related to radius of heavy meson. And yeah, we assume this radius is 0.9 Fermi. And this Wigner function is multiplied by 4, 1 plus 3, to include not only pseudoscalar meson, but also a vector meson like this star, and divide by 36. Yeah, 6 times 6, and each 6 is responsible for color factors and spin factor. And this is P wave Wigner function. We multiply it by 8, 3 plus 5 to include 1 plus state and 2 plus state, and divide by 36 again. And we assume this P state to decay to D or D star plus pion as soon as they are hadronized. And the DS or DS star are similarly treated in our simulation. And this is total, yeah, this black line is total coalescence probability as a function of transverse momentum. And it is quite low, almost 20%. This coalescence model assumes instant transition, but if we repeat, yeah, nevertheless, if we repeat this coalescence, we can increase the coalescence probability. So how is it realized in PHSD? When the local energy density is 3 quarters GeV per cubic Fermi, then we start coalescence. We try coalescence, and the repeat coalescence again and again until local energy density reaches 0.4 GeV per cubic Fermi. And if some quark still does not do coalescence, then we force that charm quark to hadronize through fragmentation, like in proton-proton collision, because eventually all charms should be hadronized. So yeah, no other way, we should force this charm to hadronize. And this right figure is total coalescence probability of charm in gold-gold collisions at RHIC energy as a function of transverse momentum. And this probability is large at low transverse momentum, but it decreases with the increasing momentum, because if charm is very fast, then it's harder to find the coalescence partner in momentum space. So it decreases. Interesting point is that it depends on centrality. If the red line is 0 to 10% central collision, and the blue line is 30 to 50% central collision, and we can see the reduction of coalescence probability. And if collision is peripheral or extremely peripheral, then this coalescence probability will be lower and lower, and it smoothly converges to PP collision. And this is coalescence probabilities of charm and bottom in gold-gold collisions at 200 GeV. The blue line is charm coalescence probability, and red line is bottom coalescence probability, yeah, as a function of the transverse momentum. And you can see bottom coalescence probability decreases slowly compared to charm quark. But if we change this variable to transverse velocity, not transverse momentum, then you can see this charm coalescence probability or bottom coalescence probability are similar. So this is just kind of artifact. I mean, if charm is less massive, bottom is more massive. So yeah, this difference comes from that mass difference. And collecting all nuclear metal effects, we can obtain the final results, and we can compare with experimental data. This is RAA of D meson, including and excluding cold nuclear metal effects. And yeah, we can see a good agreement with experimental data. And right figure is RAA of B meson. And this is RAA of a single electron and electric flow. And again, at low transverse momentum, single electron from D meson decay is dominant, and at large transverse momentum, B decay is more dominant. And let me move to dielectron. The dielectron is exactly same as single electron production, except that we have one more weak decay. But one interesting point is that we can study the correlation of a single electron and single positron, because it is important because it changes invariant mass spectrum of dielectron. I mean, yeah, I'll explain soon. This is azimuthal angle correlations of heavy flavor and anti-heavy flavor. This pi is the azimuthal angle between heavy flavor momentum and anti-heavy flavor momentum. So 0 means co-moving, and 1 means back-to-back. And this dashed line is the correlation of initial charm and anti-charm in central gold-gold collisions at 200 GeV. And it is rather flat, though it is a bit biased at back-to-back collision. But after heavy ion collisions, this correlation changes, like this solid line. Yeah, the solid line is the correlation of final D meson and anti-D meson. And we can see the correlation is enhanced in same direction and suppressed in opposite direction. And we can see same change for bottom. Yeah, this is bottom correlation. The dashed line is initial correlation, and we can see different from this charm. The correlation is strong in back-to-back direction. But after heavy ion collisions, this strong correlation is destroyed, and it becomes rather flat. And let me explain why correlation is enhanced at 0 and suppressed at 1. Heavy flavor, yeah, pair is produced at the same point. Yeah, they are together initially, heavy quark and heavy anti-quark. And then each heavy quark and heavy anti-quark has random kick or random scattering. So each heavy quark and heavy anti-quark has independent Brownian motion. But the lifetime of fiber is limited, so they cannot be separated far away. They are still nearby. I mean, yeah, some pair could be distant, but mostly nearby. So they are boosted by the same direction of flows. So by this flow, correlation is enhanced around pi equals 0. I mean, co-moving is enhanced. So we tested this idea by placing this anti-heavy quark at opposite position. I mean, x position of charm equals minus x position of anti-charm, and y position of charm equals minus y position of anti-charm. Then what happens? Initial correlation does not change because we change the position, not momentum. So initial correlation is same, but after heavy ion collisions, we obtain this new correlation, which is quite different from this one. Now, correlation is suppressed at 0 and enhanced at 1. And the reason is following. As I said, we moved this anti-heavy quark to opposite position. So now this quark and anti-quark are boosted by the opposite direction of flows. So as a result, correlation is enhanced around pi equals pi. And we also studied the effect of initial angle correlations. We assumed heavy flavor is pair is always produced back-to-back. Then initial correlation function will be a delta function at pi equal 1. And bottom is the same. This is delta function. But after heavy ion collisions, this sharp correlation function becomes like this, smeared. I mean, this solid line. And comparing with this left figure, quite different, this line and this line. So it tells us that the initial angle correlation could be important, especially for study of dielectron. And we also studied the effect of collision energy. The left figure is SPS energy, and the right figure is RHIC energy. And dashed line is initial correlation, and the solid line is final correlation. And we can see the correlation changes more at higher energy. And this difference is seen in invariant mass spectrum. This is invariant mass spectrum of dielectron from heavy flavor pairs. Left figure is SPS energy, and right figure is RHIC energy. And this blue line is without hot nuclear matter. So we switched off partonic scattering and hadronic scattering, but red line including hot nuclear matter. So we have partonic scattering and hadronic scattering. But at SPS energy, there is not so big differences between blue line and the red line. But at RHIC energy, we can see considerable suppression of invariant mass spectrum of dielectron at large invariant mass. And what we have found is following: random scattering dissipates the azimuthal angle correlations. Destroys azimuthal angle correlations. So it makes azimuthal angle distributions flat, independent of angle. However, collective flow enhances azimuthal angle correlations at pi equals 0, same direction or co-moving, and suppresses the correlations at pi equals pi, suppresses back-to-back correlation. And the initial azimuthal angle correlations are important for dielectron study, and the azimuthal angle correlations are more changed in higher energy collisions. Let me summarize my talk. In the Parton-Hadron string dynamics, initial charm spectrum and rapid distribution from PCR are tuned or rescaled such that they are similar to those from Fornell calculations. And the Peterson's fragmentation function is used for the hadronization of heavy quark in PP collisions. And the shadowing or anti-shadowing effects are implemented by EPS09. And in heavy ion collisions, Parton interactions are realized by a dynamical quasi-particle model and its hadronization through either coalescence or fragmentation, and the hadron interactions by T-matrix method. And experimental data on single electron can be explained within the Parton-Hadron string dynamics, and extended to dielectron, the azimuthal angle correlations are very important and need to be carefully treated. Thank you for your attention.
Thank you very much, Taesoo, for this very clear presentation. Are there any questions in the room? Andrea, I come to you.
I have two questions. One is on slide 25. Here, I didn't get, so the left plot is really at 17.3 GeV.
Yeah.
I didn't fully get why you have this initial CC bar correlation peaking at 0 at that energy. It's, I would have trivially, maybe naively expected that at very low energy, this would have been more back to back.
Yeah, I don't know. Just I obtained from PCR simulation, and sorry, I don't know the inside of
maybe
PCR.
you can.
Yeah, but ignoring this initial correlation, we can compare only final correlation. We can see more strong slope here compared to this one.
No, but it's the initial one on the left.
I can explain initial correlation, but I can explain final.
Is there a, sorry, no, maybe, is there any momentum cut here for the CNC bar?
No, I didn't introduce momentum cup.
So it's
Maybe if
integrated.
I introduce momentum cup, yeah, it will be changed.
Yeah, okay, now. And the second question is very interesting. I was wondering whether you can, you already looked at an eta, what happens. So in delta eta between the CNC bar.
Delta.
Eta correlations. Pseudo rapidity, yes, sorry.
You mean?
No, looking at
rapidity correlation. No, we didn't study that correlation.
Okay. But that would be also interesting.
Yeah.
Okay, thank you.
Fabio?
Just a detail on this point. But these predictions are for a single CC bar pair, or you consider the number of expected pairs per collision? Because
we know which we can trace all heavy flavors, so we know this but this B measure, this D measure, and this D bar measure come from same origin or different origin.
So
we know,
the same as you
and
correlate.
we only compare the same origin.
Thanks.
So further questions in the room? Yes, Giuseppe. Outside is still silence.
Well, I had also a similar question on the chat. It's maybe on your slide 15, you have a formula where you implement your probability for coalescence. Maybe my question is very naive or very, sorry, 14, the one before. This here, essentially, probability to have this coalescence is proportional to the relative difference in the momentum in the reference frame. Should it be more on the relative velocity or not? How do you build the final momentum of your object after this coalescence process takes place? I don't know whether this is formulated correctly.
First, we moves to centermass frame. Yeah, we can take into account all possible pairs, and for each pair we move to centermass frame of that pair and calculate this R and P, and then we obtain the coalescence probability.
Then you respect conservation of moment in the final.
Yeah, this three momentum is not Lorentz invariant, so.
Okay, that seems to be it from the room. I don't see any raised hand in Zoom. That means we can thank Taesoo again and move on.